everybody. Next up is Gabe Rogers. He's going to be talking about guidance and control, pointing the spacecraft and so on. Gabe, the floor is yours. Looking forward to your talk.
Thank you very much, Michael. Good morning, everybody. I am Gabe Rogers, and I'm going to talk a little bit about how to actually point the spacecraft so we can do all of the things that the previous panelists have been talking about. So next slide. So I hope to sort of convey the different capabilities of what a guidance and control system can do for the three proposed different science payload capabilities and the three different trajectory options. For definition, heliophysics is in a spinning only configuration with long wire booms. The augmented capability has dual mode capabilities with much shorter flexible structures. And then there we've been talking a little bit about the solar over stack. And then I'll go into some of the discussions about challenges for designing a system that lasts for 50 years. So next slide. So the three possible configurations for science, helio only, augmented, and solar over Earth, are going to determine what the GNC system consists of. In addition, the three proposed trajectory profiles for the Interstellar Probe spacecraft, unpowered Jupiter flyby, powered Jupiter flyby, and solar over Earth, all are also going to determine the way that we control the spacecraft and the hardware that we fly with us. The algorithms, concepts of operation, and all of that is dependent upon whether we're always spinning or whether we have a three-axis operations. Those define our pointing requirements. If we do a helio-only mission, then the RF system will be define the driving requirements, and that was something that Dave has been talking about the previous mode. If we have a three-axis component, then we have to take into consideration any of the instruments on board and what their pointing requirements are. And so we will have to have maybe additional hardware to accommodate for those. I'm going to present one of the particular challenges we have on this mission, which is incorporating long, flexible wire booms into a spinning spacecraft, and then trying to maintain control out to for the next 50 years or 500 years. I'm also going to talk a little bit about how you need to control between a three-axis spacecraft and how the moments of inertia will affect that. Next slide. So as Jim has presented, we have our three different trajectory options: unpowered, powered, and solar over. The unpowered flyby would be spinning. All the deployments would occur shortly after the separation of the SRM at Earth. And so it would be what I would consider a standard deployment. Everything would be enclosed, so we would have low gain antenna contact during the deployments. If you had to do a powered flyby of Jupiter, then we would have to carry the solid rocket motor all the way out to Jupiter to ignite at Jove to perform the gravity assist. And so there would be, in this case, essentially two separate phases of the mission. The first phase, we would have to control the stack after launch all the way out to Jupiter, conduct the solid rocket motor burn, and then spin up and deploy all of the science instruments after Jupiter. So there would be a completely different set of hardware that we would need to carry for that first phase than we would, well, not completely set, but different hardware for the first phase and then the second phase. And the solar over Earth maneuver is even more complicated because of the large heat shield. We could not be spin stabilized until after the shield and SRM have been separated. So this GNC spacecraft would need to control through Jupiter all the way through the sun and then out to separation again, and then it would need to spin the spacecraft up and perform science observations for the rest of the mission. For all options, the spacecraft is going to be pulling over 7 Gs during the solid rocket motor maneuver, so no structures should be deployed before the maneuver. If they can't support their own weight in 1 G, then they're definitely not going to be able to be deployed during a 7 G maneuver. Next slide. So now I'm going to talk about the spinning only configuration. Next slide. This concept assumes the spacecraft is always spinning from the SRM separation until the end of the mission. And the driving requirement is essentially the RF system. The baseline spacecraft requirements basically incorporate a large, relatively fixed X-band antenna. This is because, as previously mentioned, Ka band is very, very tight unless we and would require active pointing of the antenna. We are looking into options for that, but it would be something that we would have to work with RF to electronically steer the beam with. Stable spinning about the high gain bore site must be maintained during all maneuvers and all phases of the mission. So if you're carrying a solid rocket motor out to Jupiter with us, we must be a major axis spinner during this. This could mean that we need to have deployable structures up to the Jupiter that would maintain a major axis moment of the spacecraft. However, that's still something we would need to look at closely. It may be required that the stack out to Jupiter is in 3-axis mode until SRM separation for stability. Next slide. Dave already talked about this, so I'm not going to touch on this too much other than our driving requirement for the baseline system is 0.2 degrees. The Ka band is much tighter for the solar oberth, and therefore would require additional steering in order to get the pointing requirement for the beam that we need. Next slide. This is an example already presented of the Interstellar Probe with its long wire booms deployed. The key feature here is the 50 meter for flexible booms. In addition, we have a magnetometer boom, which will also have some effects on the spacecraft during procession maneuvers. Next slide. So there are 3 effects that you have to worry about for a spinning spacecraft. The first is coning. Coning is a constant effect that basically is an offset between the major principal moment of inertia and the spacecraft body axes, in this case, the high gain antenna. This is constant, it never damps, though it can change over the lifetime of the mission as the mass properties of the spacecraft change. It can be compensated for by shifting the high gain antenna bore site in the body axis. This would require either a mechanical steering device or maybe possibly an electronic steering device. And as it never damps, time's not really an effect here. The second is nutation. Anytime that you introduce a force or torque onto the system, you can kick up nutation. This is a transient effect that damps over time on the order of hours. And the damping is due to energy being removed from the system by either friction between things like propellants or passive nutation dampers inside the hub of the spacecraft. The pointing of the high gain antenna is going to be affected by nutation until nutation is damped. So our data rates would be lower while we've got active nutation going on with the main hub. And the third and the biggest effect is higher order modal frequencies. This is the impact of those wire booms on the structure and how they affect the pointing of the high gain antenna right after a maneuver. The stiffer the booms, the quicker the booms will damp out. However, long, flexible wire booms damp out very slowly over days. So again, after a procession maneuver, any communication with the Earth is going to be decreased as the long wire boom motions slowly starts to damp out. Next slide. The following is an example of coning, and it looks like the movie at the bottom is not playing. But the New Horizons spacecraft had coning shortly after launch. Coning was basically due to a small shift in the masses pre-launch to post-launch, and that was about 1/4 of a degree of coning which was introduced. Again, if you remember, our baseline is 0.20 for Interstellar Probe. So any shifts in the masses of the spacecraft between launch and deployments could introduce coning that will have to be compensated for. And I'm sorry that you can't see the video at the bottom. Next slide. Here's some examples of what coning could be introduced based upon the deployment of the booms. If one of the booms loses its tip mass, that would introduce roughly about 0.3 degrees of coning. If a boom during deployment is stuck, but while the other 3 booms are fully deployed, that could introduce 0.325 degrees of coning. And if one of the booms is stuck midway and we know about it, we're able to compensate by not deploying its matching boom, then we can introduce as little as 0.1 degrees of coning. In all cases, I just wanted to show how deployment of the booms could possibly introduce this effect that we need to compensate for. Next slide. The following plot is an example of mutation and how it damps over time. This is an example for New Horizons right after launch. This, again, mutation time constant of the hub will vary anywhere from 3,000 seconds up to maybe, say, 30,000 seconds, so on the order of hours. During this damping effect, the pointing of the high gain antenna is on the Earth is degraded until eventually mutation damps out and all you're left with is coning. Here are the higher order modal effects that occur when you introduce a force onto the spacecraft. The one that we're worrying about right now is mode 3, which is this mutual procession. This is the one that will take days to damp. So next slide. The following plots are from the Van Allen probes, which are a really good analog for what interstellar probes dynamics would be during flight. On the right, you can see how the higher order mutation dampens out over the course of about 3,000 seconds, and that all you're left with is the lower frequency damping. Next slide. And this shows how the damping occurs. It takes days. The little spikes are when the spacecraft went into eclipse, and that's the motion from the spacecraft heating up and cooling down. But it takes Van Allen probes about 2 days to effectively damp out the motion of the booms, at which time you would have degraded data rates for interstellar probes. Next slide. And this one is, okay. The green squiggle is the motion of the high gain antenna during a procession maneuver for the Van Allen probes. And this is a similar motion that we would see for interstellar probe every time we would do a procession. I just wanted to show how in this particular case, we were introducing about 0.25 degrees of motion of the high gain antenna. So you would have degraded rates immediately after a procession maneuver that would dampen the time. Next slide. Another issue with the wire booms is deployment. Deployment is an extremely long, intensive process that spans days, if not weeks, because we have to be very careful about deploying the booms symmetrically so that they don't introduce the coning that I had talked about earlier. The plots below are an example of the deployment of the booms for Van Allen probes. These basically consist of a series of small deployments of the booms and then a series of spin-up maneuvers, because as you deploy the booms, the spin rate of the spacecraft spins down, and you have to maintain a certain minimum spin rate to keep tension on the booms. If we are doing this right after Earth, it could take on the order of days to deploy. If we do this after Jupiter, when round trip light time is around 100 minutes, it could take much longer, because after each deployment, you have to make sure that everything deployed as expected before proceeding on to the next step. So very time intensive. Next slide. I'm not going to go into these. This is just the challenges. They require spin stabilization. They can affect coning. They can break, which could theoretically endanger the mission. Booms have broken in the past. They do increase the propellant usage. They decrease the downlink rates until damped. And there are several papers out there if you want to look into the detailed documentation of how boom motion will affect high gain antenna point. Slide. One of the other issues is the high gain antenna booms can change the coning over time. It is not a static system. The booms can contract and expand as they age. And Van Allen probes saw significant changes in the alignments of the body mounted sun sensors over a 6-year lifetime. So similar shifts could affect our high gain antenna bore side pointing, which we would need to compensate for after launch. Next slide. This just shows how the high gain or how the spin axis changed for Van Allen probes as a function of the mission of the lifetime. So it was fairly constant for the first 1,500 days of the mission, and then after 1,500 days, you could see there started to be a shift of about almost 1 degree that happened. Next slide. So again, a summary of the wire boom challenges. It does take more propellant to deploy these booms. It takes a long time to deploy the booms. It requires constant monitoring of the spin axis. In the event of migration of the moments of inertia, data rates do decrease. And if a boom breaks, that could endanger Group 1 science or the mission. I'm not saying that long wire booms are not feasible. They are very feasible, but there's something that we have to take into consideration and monitor closely throughout the life of the mission. Next slide. Now I'm going to talk about the augmented case or a dual mode interstellar probe spacecraft. So this is the configuration. The 50-meter wire booms have been replaced with 2.5-meter rigid spacers. This is going to make the dynamics during spin mode much better for us. ISP would spin most of the time to preserve consumables and operational life, but would spin down to 3-axis mode for planetary flybys and any distant KVO observations. Next slide. So the considerations, we still need to use thrusters for control. Reaction wheels are not viable for 50 years. Propellant used is also a function of the number of times that we spin up or spin down. So how the spacecraft is controlled during encounters will affect how much downlink we have during the 3-axis mode is going to affect our consumables. In addition, thrusters can fail over time, so we need to be very judicious about their use and make sure that we're maintaining their operational life. During spin mode, a dual mode spacecraft can power off GNC sensors and processors, so that is going to extend the life of the mission. Also during 3-axis mode, the spacecraft can compensate for the shift in the principal axis by just changing its bore site. So it does mean that we can actively communicate with the Earth through that fixed high gain antenna just by changing onboard parameters. There are flexible loads due to the high magnetometer boom and the 2.5-meter spacers that we have to compensate for, and they need to damp out before an image can be collected. So this means the spacecraft will be less agile than New Horizons, but we can simulate that and accommodate it for any flybys that we have. Next slide. Finally, talking about the Sun Oberth. Here's the drawing that you've seen before. You can skip to the next slide and I can talk to some of the things. So operational considerations. The spacecraft needs to maintain 3-axis pointing in the stacked configuration until deployment. The shield does prevent communications in certain directions, and the SRM does prevent instrumentation in certain directions. So we have to be very careful where we place our attitude control sensors, such as star trackers and sun sensors, because they won't be able to look through these different stack configurations. Supplemental thrusters are going to need to be required for attitude control in the stacked phase. Half of the spacecraft is shaded by the shield, the other half, the bottom deck, is shielded by the SRM. So additional stack thrusters need to be provided to give us full 3-axis control. We need to have additional redundant processors and sensors on board, which reduces the efficiency of the maneuvers because it's going to need more mass. This is because we need to make sure that we always have the attitude of the spacecraft so that we don't accidentally tip the shield a little bit and illuminate the spacecraft when it's very close to the sun. This is something which Solar Probe has done, and so we would follow sort of that methodology. The shield has to be pointed at the sun within a few degrees during the large solid rocket motor maneuver, and any pointing error would end the mission. And the spacecraft will be slewing quite quickly during the maneuver to keep nadir to the sun as we fly by, because it's a very tight orbit, and we need to track that angle. So as mentioned before, we have to add ballast mass to minimize or eliminate any migration at the center of mass during the burn. And the hardware also has to be developed to operate at 3 solar radii. That includes illumination of background dust that the star trackers have to be able to see through. And the sun sensors have to be able to survive brief illumination if we want them to work. Next slide. And finally, I got lifetime considerations. So this is my last one. We need to limit consumables. To design a system that will operate for 50 years, we need to limit operational hours on the hardware. So keep our sensors powered off as much as possible. We need to keep things simple and robust. Limit any moving parts, including gimbals, reaction wheels, slip rings, or mechanical gyros. They all degrade over time. So electronic steering is better. Add as much redundant hardware as mass will allow. Keep our software simple and up to date, because it's going to be hard to maintain ground software for 50 years. And have a personnel transition plan. So we need to make sure everything is well documented, no matter how trivial, so that the designers who will not be around at the end of the mission can pass on that knowledge to the next generation of PNC engineers. So, next slide. I can skip over this one. Next slide. So the driving point requirements for most of the mission are to ensure that the HGA maintains planes of Earth. Secondary is for planetary flybys. And balancing of the masses is the most critical thing, item to mission success. Migration can lead to loss of group 1 science. It is difficult to support Ka-band communications, and we would need electronic steering, and the long flexible wire booms do add risk. The more complicated the system or the mission, the more massive the GNC system, and the more risk that we add to the system. So that is my presentation. Thank you very much. I'm out of time, unfortunately. So.
Thank you very much, Gabe. You covered a lot of material in a quick time. If folks are interested in more information about it, there will be a lot of this written into the mission concept report coming out, as well as papers that Gabe and the GNC folks have published at Big Sky last year. And I believe, Gabe, you've got a paper coming up again this year at Big Sky on some more of the analyses.
Not yet.
Not yet.
But more to come.
More to come. All right. Great. Thank you very much.